metals and non-metals. If we look around us, we can see a large number of materials or things of different shapes, sizes and textures. We know that anything which occupies space and has mass is called matter. For example, chair, eraser, bucket, shirt, spoon, car, train and shoe. We can divide matter into pure substances, element and compound and mixture. Element is a substance which cannot be split up into two or more simpler substances by usual chemical methods of applying heat, light and electric energy. Iron, oxygen, magnesium, etc. are examples of elements. Elements can be classified into metals, non-metals and metalloids, depending upon their physical and chemical properties. Metals, iron, copper, tin, gold, etc. are metals. In general, metals are hard and shiny in appearance. Non-metals, sulphur, phosphorus, hydrogen, oxygen, nitrogen, carbon, etc. are non-metals. In general, they are not so hard. Most of them have dull appearance. Metalloids. Some elements have certain properties of metals and some properties of non-metals. These are known as metalloids. Arsenic, antimony, silicon and germanium are some examples of metalloids. Occurrence of metals and non-metals. The Earth's crust is the main source of metals and some non-metals. Almost all the rocks contain some metallic minerals. Those minerals from which metals can be extracted conveniently and profitably are called ores. In the ores, certain impurities are present along with metallic minerals. These impurities are called gangue. In the Earth's crust, metals are found in their combined states as minerals or in free states. The occurrence of metals depends on the nature of the metals and their reactivities. For example, iron, copper, etc. and gold, platinum, etc. are found in free state. Non-metals exist in the Earth's crust in combined state as oxides, carbonates, phosphates, etc. Some non-metals exist in free as well as in combined states. For example, oxygen occurs in the free state in the atmosphere. Oxygen is also present in the combined state in water. Noble gases exist only in free state. A few metals like sodium, potassium and calcium are also found in seawater. Iodine is a non-metal found in seawater. The series of processes carried out to extract pure metals from their ores is called metallurgy. Some important ores are bauxite, Al2O3, 2H2O, iron pyrites, FeS2, hematite, Fe2O3, 2H2O, and copper glance, Cu2S. Physical properties of metals and non-metals. Physical state. Most of the metals are solids at room temperature. Mercury is the only metal known to occur in liquid state in nature. Non-metals are generally solids or gases. Non-metals like sulphur, phosphorus, carbon are solids. Non-metals like hydrogen, oxygen, nitrogen are gaseous. Malleability and brittleness. The property which allows the metals to be hammered into thin sheets or foils is called malleability. Most of the metals are malleable. Gold, silver, aluminum and copper are highly malleable metals. Because of this property of metals, they are very useful to us. For example, aluminum foils are widely used for safe packing of foodstuffs, medicines, chocolates, etc. However, zinc metal breaks into pieces on hammering, so zinc is brittle in nature. Non-metals are non-malleable as they cannot be beaten into thin sheets on hammering. Rather, they break up into small pieces. The property due to which non-metals, if in solid state, break up into pieces on hammering is called brittleness. Non-metals are generally brittle. For example, sulphur and coal break up into small pieces on hammering, but some non-metals such as hydrogen H and oxygen O in gaseous state and bromine Br in liquid state do not show the property of brittleness.
Malleability and brittleness. Activity 1. To show that metals are malleable and non-metals are brittle. Things needed. Small pieces of aluminium, copper, iron, coal, pencil lead, sulphur, a block of iron and a hammer. Method. We take a piece of aluminium metal, place it on a block of iron and beat it. With a hammer, we must take care that we do not hurt our fingers while hammering. We find that the piece of aluminium metal turns into a thin aluminium sheet without breaking at all. Similarly, we observe copper and iron also flatten due to hammering and turn into thin sheets without breaking at all. However, the coal piece, pencil lead and sulphur piece broke into smaller pieces and then formed powder when beaten with a hammer. Conclusion: metals like aluminium, copper and iron can be turned into sheets without breaking when beaten with a hammer. Metals are said to be malleable, whereas non-metals like coal, pencil lead, both are forms of carbon. Sulphur are turned into powder when beaten with a hammer. Non-metals are said to be brittle. Ductility. Most of the metals can be drawn or stretched into thin wires. The property which allows the metals to be drawn into wires is called ductility. Gold and silver are among the best ductile metals.
Copper, aluminum, iron and magnesium metals can easily be drawn into thin wires, so they are very ductile. The wires inside the electric cables are mostly made of copper metal. Tungsten is used for making the filament of bulb. Non-metals are not ductile. When stretched, non-metals like sulphur and phosphorus break into pieces and do not form wires. Luster. Most of the metals are lustrous, that is, they have a shiny surface.
This property is called metallic luster. The shiny surface of metals makes them good reflectors of light. Because of their metallic luster, gold, Au, silver, Ag, and platinum, Pt, metals are used for making jewelry and decorative articles.
The glass mirrors have a thin coating of metal like silver or aluminum at their back, which acts as a reflector of light.
Non-metals cannot be polished like metals. They are dull in appearance.
Conductivity of heat. Metals are good conductors of heat, whereas non-metals are poor conductors of heat. For example, silver is the best conductor of heat, followed by copper. Aluminum and iron are also good conductors of heat. For this reason, metals like aluminum, iron and copper are used for making utensils and water boilers. However, bismuth is a poor conductor of heat. Non-metals are poor conductors of heat. Diamond, a form of carbon, is the only non-metal which is a good conductor of heat. Hardness. Metals are generally hard. For example, iron metal is very hard and strong. So iron metal in the form of steel is used in the construction of bridges, railway lines, machines, etc. However, sodium and potassium are soft metals and can easily be cut with a knife. Non-metals are not hard or strong. Density. Metals have high densities, but sodium and potassium have low densities. Non-metals have low densities and are very soft, but diamond has high density. Conductors of electricity. All metals are good conductors of electricity. Silver metal is the best conductor of electricity. Copper wires are used in household electric wiring, and aluminum wires are used in electric cables because copper and aluminum are good conductors of electricity. Non-metals are poor conductors of electricity. For example, sulphur and phosphorus are non-metals and they do not conduct electricity. However, graphite is a non-metal which is a very good conductor of electricity. Tensile strength. Metals usually have high tensile strength. The property which allows a substance to bear a lot of strain without breaking is called tensile strength. For example, iron can bear a lot of strain without breaking. Thus, it is used in construction of bridges. However, zinc has low tensile strength. Non-metals have low tensile strength, so they break easily. However, carbon fiber has high tensile strength.
Conductivity of electricity. To show that metals are good conductors of electricity and non-metals are poor conductors of electricity. Things needed: an electric cell, an electric bulb, a key, connecting wires, copper piece, aluminium piece, iron nail, coal piece, sulphur piece. Method: we make an electric tester by connecting a cell, an electric bulb, a key, and connecting wires to test whether electricity can pass through an object or not. We connect an iron nail in the circuit. We will notice that electric bulb glows. We will notice that the electric bulb also glows in case of materials made of aluminium and copper. We connect a coal piece in the circuit. We notice that the electric bulb does not glow. Similarly, the bulb does not glow in case of sulphur also. Conclusion: metals like iron, copper, and aluminium are good conductors of electricity. Non-metals like coal and sulphur are poor conductors of electricity. All the metals are good conductors of electricity. Silver metal is the best conductor of electricity.
Sonority. When we push a wind chime, it produces a sound. When the metal pipes in a wind chime strike each other, they produce a ringing sound.
The property of producing a ringing sound by metals when they are struck with a hard material is called sonority.
Thus, metals are sonorous. For this reason, metals are used for making bells. Metal wires or strings are used in musical instruments. Non-metals do not make a ringing sound when we strike them. Thus, non-metals are non-sonorous. Melting and boiling points. Metals generally have high melting and boiling points. For example, iron metal has a melting point of 1535 degrees Celsius. However, sodium, potassium, mercury, and gallium have low melting points. Non-metals have low melting and boiling points. For example, the melting point of sulphur is 115 degrees Celsius. However, diamond has a very high melting point. Chemical properties of metals and non-metals. Generally, all the metals show similar chemical properties, but their reactivities depend upon their nature and reaction conditions. Metals are different from non-metals depending upon their chemical reactivities. Reaction with oxygen. Metals react with oxygen to form metal oxides, which are basic in nature. Most of the metals are basic oxides. Reaction with water. Metals react with water and displace hydrogen from water to form metal hydroxide or metal oxide and hydrogen gas. Some metals react with cold water, some with hot water, and some others with steam. Let us perform an activity to understand the reaction of metals with water. Reaction with acids. Metals react with acids to form their respective salts and hydrogen gas. Zinc plus sulfuric acid reacts to give zinc sulfate plus hydrogen gas. Magnesium plus sulfuric acid reacts to give magnesium sulfate plus hydrogen gas. Reaction with bases. Metals react with bases to form their respective salts and hydrogen gas. Let us study how metals react with bases. Reactions of non-metals with bases are complicated. We will study these reactions in higher classes. Displacement reaction. From the metal reactivity series, we know that when a more reactive metal is added to the salt solution of a less reactive metal, the more reactive metal displaces the less reactive metal from its salt solution. Such a chemical reaction is called displacement reaction. In other words, the displacement reaction is a chemical reaction in which a more reactive element displaces a less reactive element from its salt solution. Let us perform the following activity to understand displacement reaction.
Activity 3. To show that metals react with oxygen to form basic oxides. Things needed: magnesium ribbon, sandpaper, a pair of fire tongs, Bunsen burner, boiling tube, water, red litmus solution. Method. We take a small piece of magnesium ribbon and clean it by rubbing its surface with a sandpaper. We hold the magnesium ribbon at one end with a pair of fire tongs and bring its other end over the flame of a Bunsen burner till it catches fire. The magnesium ribbon starts burning with a brilliant white light to form a powdery ash, which is magnesium oxide. We put this magnesium oxide ash in a boiling tube. Add a little water and shake it. We find that magnesium oxide dissolves in water partially. We now add some red litmus solution to the boiling tube and observe the change in color. Observation. We see that red litmus solution turns blue. This shows that magnesium oxide is basic in nature because only basic substances turn red litmus blue. The chemical reactions involved in the above experiment are given as: when magnesium metal burns in air, it combines with the oxygen of air to form magnesium oxide, which is a basic oxide. Magnesium, a metal, plus oxygen from air, burns with a dazzling white light to give magnesium oxide, basic oxide. Magnesium oxide dissolves in water partially to form magnesium hydroxide solution, base. Conclusion. Metals react with oxygen to form basic oxides. Activity 4. To show that non-metals react with oxygen to form acidic oxides. Things needed: sulphur powder, deflagrating spoon, Bunsen burner, gas jar, red and blue litmus paper. Method. Sulphur is a non-metal. We take a small amount of sulphur powder in a deflagrating spoon and heat it over a flame. As soon as sulphur starts burning with a blue flame, we introduce the deflagrating spoon in a gas jar. Sulphur burns in the air of gas jar to form a pungent smelling gas, sulphur dioxide. We keep the gas jar covered with the lid to ensure that the gas produced does not escape. We remove the deflagrating spoon from the gas jar after some time. We add a small quantity of water into the gas jar and quickly replace the lid. We shake the gas jar to dissolve sulphur dioxide gas. We now pour the water having sulphur dioxide gas dissolved in it in a Petri dish. We check the above solution obtained with red and blue litmus paper. We see that the blue litmus paper turns red. This shows that sulphur dioxide gas is acidic in nature because only acidic substances turn blue litmus to red. The chemical reactions involved in this experiment are: when sulphur burns in air, it combines with the oxygen of air to form sulphur dioxide, which is an acidic oxide. Sulphur, non-metal, plus oxygen from air react to give us sulphur dioxide, acidic oxide. Sulphur dioxide dissolves in water to form sulphurous acid solution. Sulphur dioxide, acidic oxide plus water react to form sulphurous acid. This sulphurous acid turns blue litmus red, showing that it is an acid and that sulphur dioxide is acidic in nature. Activity 5. To show that when a metal reacts with water, hydrogen gas is formed. Things needed: a sodium metal piece, filter paper, 250 ml beaker, blue litmus paper, red litmus paper, some water. Method. We know because sodium metal reacts vigorously with oxygen and water, it is therefore stored in kerosene. We cut a small piece of sodium and remove the kerosene by pressing the piece between the folds of a filter paper. We take a 250 ml beaker. Fill half of it with water. Now, put the piece of sodium into the beaker. Observation: the sodium metal floats on the surface of water and at the same time melts to form a silvery white ball. The silvery white ball of sodium darts over the surface of water with a hissing sound, producing tiny bubbles of hydrogen gas. The silvery white ball gradually becomes smaller in size and catches fire. It burns with a golden yellow flame. The solution becomes hot. This is because the heat evolved in the reaction melts the sodium metal and the hydrogen gas produced catches fire. After this reaction, if this solution is tested with blue and red litmus paper, the red litmus paper turns blue. This shows that the solution is basic in nature. The chemical equation involved in this activity is given as sodium plus water reacts to give sodium hydroxide plus hydrogen gas plus heat. Conclusion: when a metal reacts with water, hydrogen gas is formed. Activity 6. To show how metal and non-metals react with dilute acids. Things needed: a magnesium ribbon, aluminium foil, iron nail, copper wire, coal piece, sulphur powder, 6 test tubes, dropper, dilute hydrochloric acid, matchbox. Method: we take samples of metals like magnesium ribbon, aluminium foil, iron nail, copper wire, coal piece, sulphur powder in separate test tubes and label them as A, B, C, D, E and F. With the help of a dropper, we add 5 ml of dilute hydrochloric acid to each test tube one by one. We observe the reactions carefully. We bring a burning matchstick near the mouth of each test tube. Observe the burning matchstick carefully. Observation: reaction of metals and non-metals with acid. Magnesium reacts quite rapidly with dilute hydrochloric acid, forming magnesium chloride and hydrogen gas. Magnesium plus hydrochloric acid dilute react to form magnesium chloride plus hydrogen gas. Aluminium reacts with dilute hydrochloric acid, forming aluminium chloride and hydrogen gas. Aluminium plus hydrochloric acid dilute react to form aluminium chloride plus hydrogen gas. Iron reacts slowly with dilute hydrochloric acid to give iron oxide and hydrogen gas. Iron plus hydrochloric acid dilute react to form iron chloride plus hydrogen gas. Copper does not react with dilute hydrochloric acid at all. Copper plus hydrochloric acid do not react. There is no reaction. Non-metals like coal and sulphur do not react with hydrochloric acid at all. Coal plus hydrochloric acid, no reaction. Sulphur plus hydrochloric acid, no reaction. Conclusion: reactive metals react with acids and produce hydrogen gas that burns with a pop sound. Less reactive metals like copper, silver and gold do not react with acids. Non-metals also do not react with acids. To show that reactive metals react with solution of bases to form hydrogen gas. Things needed: a test tube, 3 to 4 pellets of sodium hydroxide, plastic spatula, aluminium foil, matchbox. Method. We take a test tube and drop in it 3 to 4 pellets of sodium hydroxide base with a plastic spatula. We add 5 ml of water and shake the test tube containing sodium hydroxide well. We have prepared a fresh solution of sodium hydroxide. To this solution, we add a piece of aluminium foil. We can see tiny bubbles of gas in the solution. Observation. We bring a burning matchstick near the mouth of the test tube. The gas catches fire with a pop sound. The pop sound indicates the presence of hydrogen gas. The chemical reaction involved in this activity is aluminium plus sodium hydroxide plus water react to give us sodium aluminate plus hydrogen gas. Conclusion. Reactive metals like sodium, potassium, aluminium react with solution of bases to form hydrogen gas.
Keep the test tubes undisturbed for about 15 minutes. After 15 minutes, remove the iron nail from the solution. What do we observe? We observe that the solution in test tube A has turned green, but in test tube B, it retains the same blue color. This is because of ferrous ions in test tube A, which came from the iron nail due to displacement reaction, whereas in test tube B, there was no nail and hence no displacement. We also observe that the dipped iron nail has become brown, whereas the other nail retains its greyish color. This is because of deposition of copper metal on the dipped iron nail due to displacement reaction, whereas the other nail was not dipped in the copper sulfate solution and hence retains its color. What is the reason behind the changes that appeared? Corrosion of metals. The process in which metals are eaten up by the action of air, moisture, or a chemical on their surface is called corrosion. When an iron object is left in damp air or moisture for a considerable time, it gets covered with a reddish-brown flaky substance. This is called rusting of iron. When a copper object remains in damp air for a long time, it reacts slowly with carbon dioxide and water of air. It loses its shine due to formation of a green coating of copper hydroxide and copper carbonate on the surface of the object. Copper plus oxygen plus water plus carbon dioxide, moist air, reacts. Copper hydroxide plus copper carbonate, green coating on object. When silver objects are kept in air, they get tarnished and gradually turn black due to the formation of a thin silver sulfide layer on their surface by the action of hydrogen sulfide present in the air. Prevention of corrosion. Corrosion of metals can be prevented by preventing their contact with air and water. It can be done as follows. Oil, grease or paint is applied on the surface because it keeps the metal away from air and moisture. A layer of zinc is deposited on the metal surface of iron object by dipping it in molten zinc. This process is known as galvanization. A layer of another metal is deposited on the surface of metal object by the process of electroplating. Alloys. Alloys are generally hard. For example, carbon is added to iron to increase its hardness. It forms an alloy called steel, which is used for the construction of ships, bridges, and vehicles. They are generally resistant to corrosion. For example, alloy of iron, chromium, and nickel is known as stainless steel. It is resistant to corrosion and is used for making cutlery, utensils, and surgical instruments.